Let us solve a simple Otto cycle problem. And this is a problem taken from chapter 7. Let's modify the problem a little bit. The compression ratio is given to be 8. Let's change it to 10. Okay, first thing first, we got to first draw the cycle on a TS diagram to understand the problem, to understand what is given to us. So before we start solving any problem, we draw the TS diagram, two constant volume lines. That's how an Otto cycle looks in a TS diagram. So these are constant volume lines. So 1 to 2 is the isentropic compression, and we know compression ratio is 10. This must be the state 1. So state 1, a lot of information supplied. Temperature at the end of combustion, so that must be the temperature here, 900 Kelvin. What else is known? That's it, and we have to find the highest pressure, amount of heat input, etc., etc. Okay, let's start by listing or evaluating temperature and pressure at each state. So state 1, what is supplied? Pressure is given, temperature is given. I'm just 20 degrees Celsius, I'm converting directly to Kelvin. And the volume at state 1 is given, 500 cc, which is 500 times 10 to the minus 6 meter cube, all in SI unit. We can use the ideal gas equation of state to find the specific volume and the mass, which we'll need later. And notice that specific volume remains constant from 2 to 3, which is given by this expression, and equals 0.84 approximately. So the mass, which is total volume by specific volume, density times volume, density is 1 over specific volume, is 5. Well, if we substitute the expression, 500 into 10 to the minus 6 meter cube, 0.84 meter cube per kg, which is very small amount. So now that we know state 2 completely, we can find, state 1 completely, we can find state 2 because it's isentropic. And we also know the compression ratio. So if we go to state 2, let's first list what we know. We know that the specific volume is, or we can write volume 1 by 10 to us, because mass is same as m1. So the relationship being isentropic, to find the temperature, we are going to use equation 11, the isentropic relationship from the PG model, which is in table J. If you go to test, table J, or your textbook, it has the handout of all the different material models. So using the equation 11, we can write T2 over T1 can be written as V1 over V2 to the power K minus 1. And V1 over V2 is nothing but R, the compression ratio, the volumetric compression ratio. And that immediately gives us T2, which is equals T1 times R to the K minus 1, and substituting the values, we obtain T2 to be this, 736 Kelvin. And the pressure, which is, we can now evaluate, because again, PV equals RT, the ideal gas equation applied to equation state 2 will tell us that P must be equals RT over V. R is 287.287 for air. Temperature we just found and we divide by the specific volume, which is 0.84. Remember, oh sorry, it's 0.084 because it's V1 over 10, and therefore pressure becomes equal to a very huge number, 2515 kPa. To verify these calculations, we launch the TESTcalc. We go back to the TESTcalc. Let's go and verify these answers. State 2, the volume is equals volume 1 divided by 10, and mass is equal. Notice that we could also write specific volume to be 1/10, but if we write mass and volume, automatically specific volume will be calculated. As a matter of fact, you cannot enter specific volume now. If you click on specific volume, you'll notice that at the bottom they will say state property V2 is now, you cannot click and evaluate it. You will see an error message. What else is known? What else is known is, in this compression process, mass remained constant, volume became 1/10, and it's isentropic, so entropy doesn't change. S2 equals S1, and now we have enough information to evaluate the state. Temperature is 737 Kelvin, and pressure equal to 2514. So that's what we obtain manually. Let's proceed. Find state 3. Again, it's a constant volume heat addition. So V is known, and temperature is given to us. So using PV equals RT again, we can find the pressure. Which turns out to be, so we found the pressure at state 3. That's the highest pressure. So I think that's one of the question. We know the highest pressure in the cycle, and temperature is already known. So let's proceed to find state 4 now. To find state 4, again we are going to use the isentropic relationship. So notice 3 is here, 4 is there. So the isentropic relationship says that the temperature ratio, say T3 over T4, and volume ratio, the opposite of volume ratio, goes something like this. And V4 over V3, notice this volume remains constant between state 1 and 4 and state 2 and 3. So V4 over V3 is same as V1 over V2. And what is V1 over V2? This is the maximum volume by minimum volume. That's R. So therefore, T4 can be obtained as T3, which is 900 Kelvin, divided by 10 to the 1.4 minus 1. And if we just quickly calculate it, it turns out to be 358 Kelvin. At state 4, notice volume remained constant between these two. I'm interchanging between capital V and small v because mass is constant. Therefore, volume capital V also remains constant, or small v also remains constant. We can quickly evaluate pressure from PV equals RT. So specific volume is same as specific volume at state 1, and you can just show that pressure turns out to be 122 kPa. So at state 4, when the exhaust valve opens, note the pressure is higher than atmospheric. That's what causes the blowdown. Immediately some gas escapes. because of the pressure difference. Well, let's go and verify them. State 2, we shouldn't proceed without verification. And at state 3 is the highest temperature of the cycle given to us, 900 Kelvin. And the specific volume, well, we can write down mass doesn't change and the volume doesn't change. Remember, the combustion happens very, very rapidly in a gasoline powered spark ignition engine. This way specific volume remains the same, or the volume and mass remains the same. At state 4, mass is always the same. It's the same mass executing the cycle. And the volume is back to the original volume 1. And of course, entropy at S4 equals S3's isentropic expansion. Oops, I made some mistake here. So at state 4, the pressure cannot be so high. So mass remains the same, volume remains the same, and entropy, what mistake did I make? Okay, I don't see anything wrong we have done here. Let's go back to state 3. Did we make a mistake here? Okay, temperature is given, 900 Kelvin. Mass is given, mass is always constant. Oh, right here, volume 3 is not volume 1, should be equal volume 2, right? From 2 to 3 is the constant volume process. Now we can see that 3071, that's the manually calculated pressure. And now if you go to state 4 and if we recalculate the state, yep, now look at the TS diagram. Because it's chosen, it automatically shows up. It looks just like what we expect. Of course, 2 and 3, if we draw the volume equal constant line, 2 and 3 should be connected, 1 and 4 are connected. So these are different constant volume and pressure lines. So as you can see, if you do the constant entropy lines and constant volume line, this is the cycle that we have just calculated, and it makes sense. All right, now that we have verified all our states, let's go and evaluate what we are after, the cycle analysis based on as far as network or thermal efficiency, etc. are concerned. Again, we draw the cycle on the TS diagram. Again, I cannot emphasize how important it is to know how to quickly convert a cycle into a TS diagram. We know heat is added here. That's our Q in that takes place in the cycle. And this is where our Q out take place, right? And it's relatively easy to figure out Q in and Q out. So therefore, we will not calculate W in and W out because we know Q in is what? We have already developed the formula, but it's obvious. A closed volume of gas is taken from 2 to 3. So it's simply delta U because there is no work. And that's mCv T3 minus T2. So if we substitute the values, our mass is 5.9 into 10 to the minus 4. CV 0.718. Again, the value for CV and K and CP for air should be known, or you can find it from any PG table, from the tables module. And T3 is 900, that was given to us. And T2 we found to be 400. How much was the T2 we found? I think 738 Kelvin. And this turns out to be pretty small, 0.069 kilojoule. Likewise, we can find Q out. Q out will be, again, the higher minus the smaller one. mCv T4 is higher than T1. These are all positive numbers. So heat transfer in a closed process at constant volume, there is no work, therefore the formula becomes really simple. Again, this is the mass CV of 718, and T4, how much was the T4? I have that in front of me. It's about 358 Kelvin minus 290 Kelvin, and that turns out to be 0.0276. Well, we can go and find W net from there, but before that let's go and quickly verify. For that we go to the process panel. Here we should calculate all the processes. Process A is our compression, isentropic compression process, where there is no heat transfer. In fact, boundary work is already calculated, but we'll still put the heat transfer to be 0, and we can see this is the work of compression. Process B will be constant volume heat addition 2 to 3, and notice the TESTcalc figures out the boundary work is 0 automatically because it looks at volume equals constant and says there cannot be any work transfer. So Q is 0.069, and I believe that's what we got, 0.069. Okay, and then we have process C, which is isentropic expansion from 3 to 4, and we know Q equals 0 is isentropic, no heat transfer, no entropy generation, as you can see, and it produces the boundary work. And finally, process D is our constant volume heat rejection from 4 to 1, and boundary work is 0 obviously, and there is, if you just hit enter, it produces the heat transfer. Again, Q is negative here because Q is algebraic, but Q out is a positive number, which will be 0.026. So let's go, what we got here, 0.027, sorry. So this is what we got here. So Q in and Q out are correct. So therefore, W net, so this is the trick we are using, W net equal Q net basically, sorry. W net and Q net are equal, which is Q in minus Q out, which is equal to (0.0417 kilojoule). So if you have to find the thermal efficiency of the cycle, of the Otto cycle, W net divided by Q in, and we can see that, show that it's about 60.2%. Let's just turn the problem slightly around and find some other numbers so that the definitions are clear. Notice W net has the unit of kilojoule. What does it mean? That means one cycle produces this much amount of work. So just suppose we have an 8-cylinder car or 8-cylinder device running at 3000 RPM. That's what your odometer in the car shows when you drive a car. So how can you convert that number into what is the power of the car? So this is from one cycle. So if you can multiply this by number of cycles, that will produce W dot net. And then if you multiply that by 8, then we'll get the total power of the cycle. In other words, so W net total equals 8 times W dot net, right? Which is 8 times, what is W dot net? N is the number of cycles times W net. Number of cycles per second, which is 8 times N by 2 W net. See if it makes sense. What is N? Number of revolution per second. By revolution I mean when you say 3000 RPM, what does it reflect? It is the number of revolution per minute of your crankshaft. And we know in a 4-stroke cycle, 2 revolutions makes 1 cycle. So number of cycles per second is number of revolution divided by 2. Number of revolution of crankshaft divided by 2. If it's a 2-stroke cycle, this 2 will not appear. So now the answer becomes 8. N is number of revolution per second, so there will be 3000 by 60, and this 2 is carried over, and W net is 0.0417, and so we get something like 8 times about 1.04 kilowatt, or it's something like 8.3 kilowatt. So it's a very small, very low power typically. So this is the academic problem, and normally this power should be about 10 times that. Okay, so we have determined the net power, we have determined the thermal efficiency, etc. I'll just quickly take a few minutes. First of all, let's confirm this answer. So we have calculated all the processes, all the 4 processes. When they are evaluated, only then you can go to the cycle panel and calculate, and it will produce all the numbers for you. So it produced, for instance, W net, so many kilojoules, Q net, maximum power, maximum pressure, etc. Everything that about the cycle that is important. Now suppose someone asks, we used PG model, which assumes Cp and Cv to be constant. What if we used Ig model? If you want to solve a problem involving Ig model, the best is to use TESTcalc, because PG model gives you the insight. You get the answer which is pretty close to realistic answer. So let's see, if we used Ig model for a more accurate answer, how the answer will differ. Well, do we need to recalculate everything from the beginning? No, there's a simpler way. Suppose we just click the super calculate button. That will produce what is called a macro or test code. You can just copy this code, Control C, and let's start, or right here, let's start the Ig model, reciprocating cycle. Instead of PG model, we go for Ig model this time. And look, it looks almost very similar, except you will not find, Cp will become a function of temperature now, as opposed to a constant. In the I/O panel, the copied code, we simply paste the code. Test code simply means what was given for the cycle. Notice pressure was given, temperature was given at state 1. Whatever we did, this is a copy of what we did in a shorthand. So once you paste it, you click the load button, and that will do the magic. All the states will be recalculated, and everything is done for you already. It's still a good idea to draw the TH diagram to make sure there is not a big surprise. 1, 2, 3, 4 looks very similar, just like the PG model. And now if you go to the cycle panel, you can pick up the more accurate answer. Look, thermal efficiency is now 58.15%. And what we got? 60%. So if we used Ig model, this go to 58% if Ig model is used. If you do manually, the Ig model will take a much longer time to solve, and the change in answer doesn't justify using such a complex model in the days of computers. So manually, the PG model is way easier to handle. And then once you verify that using TESTcalc, make it a habit to carry the test code. And if you're curious, find out how the answer will differ if you're really keen for accurate answers. But now, look at the beauty of this. If you just have a what if scenario in mind, suppose you say, okay, we used a compression ratio of 10. what if we could use a compression ratio of 15? You're designing the engine and you say, I'm going to use a bigger compression ratio. We know compression ratio from theory that higher compression ratio means higher efficiency. So let's see if it is really true. So just hit the super calculate button after we change the compression ratio. Go to the cycle panel and notice the thermal efficiency is, where is the thermal efficiency? Is 64%. So as the compression ratio increases, thermal efficiency went from 58 to 64% for R equal 15. So as you can see, higher compression ratio means higher efficiency as known from theory. And we'll learn more about this soon in our next module.